Hello, my name is Toshiaki Koike-Akino from Mitsubishi Electric Research Laboratory, MERL, in USA. Today, I'd like to talk about our new proposal named AutoVAE, which uses irregular posterior-prior pairing. First, I'm going to review trends of generative AI, artificial intelligence, specifically Bayesian inference based on variational autoencoder. Then discuss generalized version for variational inference, which may allow various posterior, prior, and likelihood beliefs, as well as discrepancy measure divergence. Then we propose automated VAE, AutoVAE. Showing some experiments, we conclude the talk. Our goal is to find a good stochastic model for VAE specifications. This figure shows Gartner hype cycle for emerging technologies. You can see many AI technologies in this chart as high expectation methodologies. In this talk, specifically, we want to focus on generative AI. AI includes diverse technologies, including classical machine learning, such as support vector machine, and recent deep learning, as well as quantum machine learning. AI shows a great success in media signal processing for audio and visual, and it even surpassed human-level performance for various applications, including gaming. When I count the number of articles in Google Scholars, I discovered a new Moore's law. For example, the research on deep neural network has been exponentially increasing over the past decade, nearly doubling every year. Similarly, the trend of generative AI follows the exponential growth. GAN and VAE are promising methodologies, which are growing at the same speed. Generative adversarial network, GAN, was proposed in 2014, which uses adversarial training to generate fake images by competing generator versus discriminator. GAN can synthesize photorealistic pictures surprisingly well. In 2014, another generative model based on variational autoencoder was proposed. We focused on this VAE. VAE uses encoder and decoder architecture. Encoder infers hidden latent variable, and the decoder is a generative model to produce the data X from the latent variable Z. The encoder and the decoder are jointly optimized to maximize the evidence lower bound, L-bar. The VAE has been used in a myriad of applications, such as generative model, Bayesian inference, dimensionality reduction, and so on. In this VAE optimizations, there are four important stochastic factors: likelihood to model reconstruction data, posterior belief to infer the latent variables, prior belief for the latent distribution, and a discrepancy measure for the pair of posterior and prior beliefs, such as KL divergence. Typically, standard VAE uses normal prior distribution for latent variable and normal distribution for posterior belief. Bernoulli likelihood model may be used as a binary cross-entropy loss. We can, of course, change those stochastic models instead of normal distribution for posterior and prior. We are interested in what happens if we use mismatched posterior and prior. In fact, there are many variants of variational inference methods using different likelihood, discrepancy, posterior, and prior beliefs. For example, beta VAE uses weighted KLD as a discrepancy for adjusting stronger or weaker regularizations for latent distribution. Continuous Bernoulli distribution was proposed, alternative to Bernoulli distribution, to show some benefit. Sparse VAE uses Laplacian or Cauchy distributions in posterior and prior pairs. And Renyi alpha distributions are also introduced, allowing such a different possibilities. Generalized VI allows any arbitrary likelihood discrepancy, posterior and prior beliefs. And we consider how to optimize such a generalized VI when allowing mismatched posterior-prior pairs by introducing automated ML AutoML framework. Standard VAE may be optimal if posterior, prior, and likelihood beliefs are well specified. However, real-world data may not follow such a specified beliefs in general. For example, reconstruction statistics may not follow closed-form distributions such as normal distributions. And also, true hidden latent variable may come from some unknown distributions. Therefore, standard LVO and KLD are no longer optimal for such a misspecified dataset. Then GVI compared different variants of discrepancy measures, for example, Renyi alpha, beta, gamma, Jeffrey, and Fisher divergence, showing that KLD is not necessarily robust enough for a unspecified data distributions. It suggests us that we have a lot of degrees of freedom to choose for stochastic factor, posterior, prior, likelihood, and discrepancy measures. However, unfortunately, finding such a good stochastic model requires a large amount of manual effort. To resolve the issue, we propose to use AutoML framework to search for stochastic model combinations besides architecture search. Our technique is more interesting than usual network architecture search because we can allow interesting pairing. The first pair is matched case when posterior and prior are both the same distribution, such as Laplacian. The second case is mismatched pair. Posterior z given x comes from Laplacian. However, prior distribution z comes from normal distribution. The last case is heterogeneous pair. z1 given x comes from Laplacian. z2 given x comes from different distributions such as normal distributions. Then prior z1 comes from normal and z2 come from Laplacian. Here, z1 and z2 are both mismatched and no longer identical distribution. Our AutoVAE uses AutoML framework to search for such a heterogeneous mismatched posterior-prior pair automatically. Specifically, we use opportuner library, which may use Bayesian optimization and hyperparameter pruning to find a good candidate. To choose posterior belief, we need to be careful to enable reparameterization trick to differentiate variational parameters mu as a location and sigma as a scale given random sample epsilon. The most straightforward choice is location scale family such as normal, Laplace, Cauchy, logistic, uniform, Gumbel, and exponential. When epsilon comes from a standard LSF, its location and scale transformed z will stay the same member of the LSF. For prior distribution, we should consider to have a closed form KLD expression. This three figures shows the landscape of 2D KLD for matched normal, Laplace, and Cauchy beliefs. Normal KLD is circular symmetry. However, Laplace and Cauchy have diamond-like landscape, which can promote sparsity for latent variables. We consider 16 different posterior-prior pairs, which have closed-form expressions, either matched pairs like normal-normal, Laplace-Laplace, Cauchy-Cauchy, and Gumbel-Gumbel, or mismatched pairs like Laplace and normal. This figure shows the KLD as a function of location mu for a different LSF function. Black curve is normal KLD. Blue curve is logistic and normal KLD, which is higher than matched normal KLD in small locations. However, there is very marginal difference in larger locations. Laplace KLD has lower KLD than normal, and mismatched normal and Laplace KLD can have lower KLD than Laplace in some region. This suggests that mismatched posterior-prior pair may be a good candidate which has a sufficiently small KLD. Actually, KLD is only a particular choice of discrepancy measure for VAE, and Renyi alpha divergence can generalize KLD towards a different discrepancy measure like chi-square divergence, Heringer distance, and worst-case regret. It was shown that alpha divergence can have tighter elbow bound, known as variational Renyi, VR bound. When we use alpha equals 0, it is known as importance-weighted autoencoder, IEEE. The last stochastic factor is a likelihood to measure the reconstruction loss. For example, if we use Bernoulli distributions, the negative log likelihood becomes binary cross entropy. We may use continuous Bernoulli instead of Bernoulli for non-binary pictures. When we consider MSE loss function, it corresponds to the likelihood belief based on normal distributions with unspecified variance. Mean absolute error corresponds to Laplace distributions with unspecified variance. Those cases uses only one variational parameter, lambda, but we may use bivariate likelihood, such as normal distribution, Laplace distribution, and beta distribution. Our AutoVAE can explore such different likelihood beliefs, as well as discrepancy measure for different posterior and prior belief pairs. Let's see some experiments for benchmark datasets such as MNIST. We consider VAE architecture uses a simple multi-layer perceptron having 400 hidden nodes and 20 latent variables. We trained VAE using adaptive momentum for mini-batch size of 1000. We evaluate multi-sample elbow, known as IEEE, because it shows tighter elbow bound. This figure shows the performance of elbow as a function of Renyi order, alpha. When alpha equals 1, it corresponds to a standard variational inference. 0.5 alpha, it corresponds to Heringer distance. And 0 is for IEEE. Black curve is normal posterior-prior pair. By adjusting alpha, we can improve elbow performance. Laplace and Laplace pair can be better than normal pair. And interestingly, mismatched pair like logistic normal and Laplace normal can be even better than those matched pair. And eventually, by using AutoVAE, allowing heterogeneous distributions, we can significantly improve elbow. This slide shows randomly generated pictures for a different pair of posterior and prior beliefs. It is hard to evaluate the quality. So people propose to use inception score. Specifically, we consider FID and KID. Then this table is a summary of the result. Each block uses different likelihood, such as unspecified normal, Bernoulli, unspecified Laplace, normal, continuous Bernoulli, beta, and Bernoulli IEEE. Each column uses different posterior and prior pairs, such as normal standard pairing. We can see that mismatched pairs, such as logistic normal, can outperform matched normal distributions. When we use AutoVAE, we verify that heterogeneous pairing can improve elbow performance for all the cases. Such VAE may use 50% logistic normal, 30% Laplace normal, and 20% Laplace. This was found by AutoML without considering brute force pairing, which may be exponentially large search space. Let's conclude my talk. We first overviewed trends of generative AI. Then we propose AutoVAE framework, which automatically search for posterior, prior, and likelihood beliefs on top of architecture exploration. We specifically allow mismatched posterior-prior pair, such as logistic posterior for normal prior, and even heterogeneous irregular pairing, such as 70% logistic normal and 30% Cauchy. Then our AutoVAE considers different discrepancy measures adjusting order of alpha. Then we also discuss diverse likelihood beliefs for reconstruction loss. We showed that the proposed AutoVAE can improve the performance for some benchmark datasets. in terms of L4 performance and also inception scores. We hope you enjoyed my talk. If you have questions, please contact me. Thank you so much.